All right. Good morning, gang. See you survived the fourth weekend. I hope you had a good time. Um, we are about done with chapter 11 here. We do have a test tomorrow. I'm going to go through a lot of that stuff, tell you exactly what's on it. And then we're going to briefly finish up chapter 11, and then we're going to do as many homework questions as you have to try to get ready for tomorrow. So here we go. Try and hang in there. I know it was a long weekend. Okay, so this is on 11.5, and it's on what's called the arc length parameter. And then we introduce something called curvature. For today. So let's see, let's get our brains back into it here. We're going to be given some vector value functions. So we've got R with as a vector function, and maybe just notationally, it could be in 2D, it could be in 3D. So we'll just go ahead and put it in 3D. So x, t, y, t, z, t. For some range of t, I'm not going to be too careful on that one right now, because I'm going to want to adjust it. Then the length, we've already seen this, the length, if we just said the length from A to B at least, it's just the square root of each of these derivatives squared. So I'm going to actually just use the prime notation, x prime, y prime, and z prime, and those are all t's, so dt is just a reminder. We take all the t derivatives here. But what I'm going to do today is, instead of doing this length, I'm just going to adjust the upper bound here. And basically the idea is it's going to end up being replace b with a variable. So if we can't make it hard enough, we're going to take bounds in integrals and turn them into variables to see what happens. Because we're not going to want to just find one length. We're going to want to find a formula that can do any length that we want along the way. So, but I'm going to do a pretty simple example here, which hopefully over time gets into your head. R of t would do sine, cosine, actually, yeah, sorry, cosine, of course, because that's x, sine, and then t. So there's my vector value function, the usual x and y is cosine, sine. But now t is in the z component. So if we draw this, yikes, x, y, z, then it does look like cosine and sine. So it does look like a circle, except the t, every time I do a unit, it goes up. So this is the spiral or the helix example, or spring, basically what it looks like. And so if we wanted to figure out the length of any sort of thing along the path, well, we just do what I said on the previous page, and I probably should just go back and fill in one little thing. We've already seen it. This turns out to be the integral of the length of the derivative, so, or the velocity in this case. So we took the derivative r prime, found the length, and then took the integral of that. It's the same thing as doing x prime, y prime, z prime, squares plus square root from a to b. So this is a nice little condensed short formula for length. So just as a reminder, if we want to do v of t as r prime, then we get our standard minus sine, cosine, and 1. So if we take the length of that guy, the length of v of t, make sure you square out the negatives. That's always a mistake people make on the homework. Then we get the square root of sine squared, cosine squared, and 1 squared, which turns out to just be 1 plus 1 inside. So that's square root of 2. So my length formula would be an integral, and then I'd be just integrating the square root of 2 dt. Now, we'll put the bounds in here. That's the general formula. Well, I guess I can just go ahead and write this out. Square root, so if I integrate square root 2, I get square root t, and then I'm going to want to put the bounds in. But let me adjust the bounds in a couple different ways. So if I went one turn of the helix, that would mean that the t would start at 0 and it would go up to 2 pi. So that's, you go around the helix once, you come back to this same point as far as x and y are concerned, you're just above it. So how far is that all the way around? Well, technically the answer would be the integral from 0 to 2 pi of my length of v. But I already know what that answer is. It's just square root of 2 t evaluated from 0 to 2 pi. I've already figured this out in general, so all I got to do is plug in the bounds, and I'll get 2 square root 2 pi. That would be the length if I went around one time. So just take the derivative, do the length, and then integrate it and plug in the bounds. And that would be for one turn. If I did 2 turns, now the t parameter just go around twice. So I'll come back to the beginning, I go around again. So I get 2 lengths of the spiral. That would correspond to going from not 0 to 2 pi, but 0 to 4 pi. So we know the length in that case is just going to be, well, probably not too surprising, we just get double what we did because we're just going around twice. So we get 4 times the square root of 2 times pi. If we wanted to do just 1/2 of a turn, so don't go all the way around, just go half, so now we're in the back of the spiral, then the t would just go from 0 to pi, and the length would be just, it would just be half, be half. So we'd be plugging in 0 and pi, we would just get the square root of 2 times pi. So you've got 3 different things which we just plugged into the square root of 2t, all without redoing the integral over and over and over and over. So we have a formula for it. So this is where we introduce what's called the arc length formula, or the arc length parameter. For this example is going to be S, because of course we need more letters in there, and letters that look like 5s, that's always a great idea. The arc length parameter in this case is just, well, what are we doing each time? If we went to 2 pi, we got 2 square root 2 pi. If we did around twice, we did 4 pi. If we did half a turn, we got pi. Each time, all we're doing is just taking square root of 2 and then multiplying it by t. And so this is your arc length parameter, or you can think of your arc length function. So this just says if you know the ending point, you just plug it in to t, and that will give you the length up to that point. So that looks pretty straightforward for this particular example. In general, all we do is it's going to be the same thing, except you just change your function here. So the general thing here is the arc length function is just the integral. So our s of t, so just like we just did, that's an s there. So try to make it as curvy as you can, I guess. Is the integral, and now you can think about it like this: from 0, or whatever the starting point is, typically 0. Sorry, in this case it is 0. Up to, we put the t in the bound, and then we take the length of v and we integrate it. And that's sort of the shorthand version of all of this is exactly this. If you want to write it out a little bit more precise, we would typically say the integral from 0 to t of the length of v, but see, that's a function, so it has a variable in here. I don't really like putting t in both places. If you're physics, take physics classes, they will do that. But this t is supposed to be the actual variable, and anything that's inside of an integral is called a dummy variable. So we can put in something here, and so typically we put in our u substitution here or our other u variable. So all this means is integrate everything with u's, but in the end you're going to be plugging in 0 and t anyway, so the answer will have a t in it at the end. So that's how you calculate s. And I'm not going to go too much in the theory because it's bright and early on a Monday morning, but I'm going to at least say why you use this is because it gives a really great way to determine how much a curve is turning. So I don't really want to go too depth into the math because again, it's not super complicated, but you can kind of get lost along the way. So we use, but the point is this: we use the arc length parameter or the arc length function to define. And this is not a technical word, but it's the sort of curviness of a curve. And in a picture, let's see if I want to do this in 3D. That, all right, we'll go ahead and do it. Is if you had your a basic curve C, and you went along at every single point, you just put in. We'll just pick a bunch of points here. If at each point you put in the tangent vector, so we want the unit tangent vector that points along there. So it's sort of like direction of the curve. So we just come in, we want to draw a little tangent vector right there. So it has length 1, it's tangent to the curve. If we went to this point here, then the tangent vector points that way. It does change from one point to the next. The tangent vector will be pointing in a different direction. And that sort of makes sense because it's turning. If we come here, tangent vector, it's just drawing in sort of all the tangent vectors. Now this one here, you'll notice at the beginning, it does curve. The tangent vector is changing. But if we get into this loop here, then you can see that at one point going into the loop, the tangent vector is pointing up and to the right. But what happens at the top? The tangent vector is sort of radically changed, and it's now pointing to the left and actually down a little bit. When we get into real loopy parts, this tangent vector is going to radically change direction. If you're in sort of a straighter part or a slightly less curved part, the tangent vector will turn and point in a different direction, but maybe not as quick. And so that's what's going to end up happening up here, is figure out how much the tangent vector changes for every 1 unit you go along. Let me just put the rest in here just for emphasis sake. All these little t's here are supposed to be tangent to the vectors. And again, in relatively straight areas, the tangent vector, like right in here, the tangent vector hardly changes at all because why? It's not very curvy. But at any time it is curvy, the tangent vector will change pretty radically. And so here's the actual definition of what's called curvature. Is you take how much does the tangent vector change every time the arc length function goes up by 1. And so how do you do rate of change? You're like, no, don't do it. It's going to be ugly. And the answer is, yeah, you do a derivative. You take the derivative of the tangent vector per unit length, which is this new thing s. You're like, there's no t's in there anymore. That's just terrible. And not only that, but this is not a number. So it's a vector. So instead of just leaving it as a vector, you take the magnitude of that guy and you call that the curvature. And to make it even worse, they don't even use a K, they use the Greek letter kappa to represent curvature. So if you're with me at this point and haven't completely nodded off, that's the idea. It's basically how fast T changes for each unit length along the curve. And that is the theory. That's the theory. Computing this out is tricky. I don't know if if you finish the homework and stuff. Finding T to begin with is a pain. It's the R divided by the derivative. Sorry, it's R prime divided by the length of R prime. You got to take that. Then you have to find S. Then you have to reparameterize everything in terms of S. Then you have to take the derivative of that T with respect to S, and then you have to find the length. And we're not going to do that because it's just way too much work. So we're going to hope that there's some sort of shortcut in here, and in fact there is. So again, I'm just going to leave it up to black magic here of math. Don't look behind the curtain, and boom, we end up getting a pretty nice formula. There's actually a couple of them. One is that you can take, it's not everything perfectly magic, but you can take the length of T prime and divide it by the length of R prime, and that gives you the curvature. You don't have SN in there anymore. You don't have to reparameterize everything. It's all back in terms of T. That's a little bit nicer. Even nicer than that is, and I'm not going to prove any of this stuff. It all comes out of algebra and a lot of paper and writing this stuff out. It turns out that instead, I don't know if this looks any nicer, but it is. You can take the derivative of R, you can take the derivative of R prime, and you can cross them together, like really, and then take the length of that cross product, and then divide that by the length of the derivative cubed. And I have seen that kind of formula in engineering texts before, so if you haven't seen it yet, it's coming up. So congratulations. Yeah, let's go ahead and we'll just go ahead and do an example of that. We have, not go too far with that example. So we did basic curve here. R of T, just to give you a reminder of all this stuff, cross products and lengths and stuff. So here's my curve. T squared and T squared over 2. So kind of looks, I'm not going to draw the curve because we could plot it out. It's in 3D. It's kind of parabolic in one direction. It looks kind of parabolic in another. If you look at X and Z. If you look at Y and Z, it looks almost linear. So try and think about like parabolic on two sides and linear in the other. I'm not going to worry about what the picture looks like. But the curvature of it is given by this formula up here. So let's just find R prime and R double prime. R prime is going to be 1, 2t, and t. And then even easier, R double prime is just 0 to 1. It's a fixed double prime. So at this point now it's just very formulaic. I need to find the cross product of these two things, find the length, and then divide by the length of R prime. Maybe just put the length of R prime here. So the length of R prime is going to be the square root, and then I just square each of these and add them together. So 1 squared, 2t squared, so that'll end up being 4 times t squared, and I square the whole thing. And then another t squared. So I'll get 1 plus 5 t squared. Just want to do the length of that vector there. For the cross product, go back to that, cross product of R prime and R double prime according to the formula here. So I make my matrix with ij's and k's. And I will get 1, 2t, and t. That's r prime. And then r double prime 0 to 1. And what does that turn out to be? In the I direction, you multiply the little subdeterminant. It'll be 2t times 1 and t times 2. Well, that's 2t and 2t. So they get subtracted out. You get 0 in the I direction. In the j direction, so you cross out the stuff that's j. Now I'm going to have 1 and 1 and 0 and t. So I go 1 and 1, that's 1, t and 0, that's 0. So I get 1, but there is a built-in negative as usual. J direction, so that's negative 1. And then for k, come down to this little subdeterminant in the bottom left corner, 1 times 2, 2 times 2t times 0, so that's just 2. Okay. So I get the vector. So you can write it like that, or write it as 0, negative 1, 2. Try not to mix the notation. On some people's homework, you were like 0i goes in here, but don't do that. It's either 0i by itself or 0 in the component. So if you put that together with this, the curvature is just going to be the length of r prime cross r double prime. So find the length of that vector there. Square root of each thing squared, so 0, 1, and 4. So that makes it square root 5. So the top is square root 5, and the bottom is the square root of 1 plus 5t squared t. So that's the curvature formula. You'll notice it still has a t in it, which should make sense because as the t changes, you'll move along the curve. Some places will be curvier than others, and that will end up having a higher curvature value depending on the position you're at. So for example, if t is 0, then the curvature will be, well, the bottom will be 1 plus 0, so the answer will be square root 5. So it's square root 5. There aren't going to be any units on this. It's just sort of a relative thing depending on where you're at.
Sir?
Yeah.
I have a question. How did you get square root of 1 plus 5t squared? I kind of missed that.
Yeah, so how do you do length? You take each of these guys and square them. So you take 1, that's the 1. What happens when you square these other two pieces? When you square 2t, the 2 also gets squared.
Yes, sir.
So that'll be 4t squared, and this will be 1t squared. So that together will be 5.
Okay, thank you.
Yeah, no problem. I don't know if there's any other good, let's try equals 1. So if t is 1, then this gets ugly, but the curvature will be square root of 5 over, and the denominator will be 1 plus 5, so that's 6. Square root of 6 cubed, I guess you could just write that as 6 to the 3 halves, which is certainly smaller because the denominator here is going to be bigger than 1. You're dividing, so that means at this second point it's less curvy. And actually, as you go out, what happens is t gets bigger and bigger. As t gets bigger and bigger, the curvature ends up going to, well, the bottom's getting bigger and bigger and bigger and bigger, so the whole thing is getting smaller and smaller and smaller. But the curvature is going to 0, which maybe you are not too surprised to learn that a straight line has 0 curvature. It's not curved, so we have 0 curvature. So as this goes along, this thing starts to stretch out and look more and more and more and more like a line as you go out. And like a parabola, and looks more and more like a line. Not quite. I shouldn't say that because this is a curved object. So it is starting to straighten out a little bit more as we go on. Okay, so there's that. And then even nicer in the special case, and this will be very good for when we're doing circles. The special case is if the curve is just in 2D. So if we don't have a third dimension component to this, then, so what this will look like is R of t will be given by something like this, x of t, y of t, or even more precisely is if we eliminate the parameter, we can get a curve that's going to look like y equals some function of x. So if we can do that, or really even if it just started with a vector in terms of x, then it turns out that we have a very nice formula for curvature. And this one definitely is in engineering text, because that's where I found this before. It turns out that the curvature, we can create r prime and cross it with r double prime and work out all the stuff from the previous formula. What you end up getting is just straight up the second derivative, which might be negative, so we have to take the absolute value of it, because we want these to always be positive. And the denominator turns out to be 1 plus I'm going to say magnitude. It's the absolute value of f prime of x squared, and then raised to the 3/2 power. So some of this stuff you can start to see. The bottom looks kind of like the r prime in the previous formula. It turns out that f double prime turns out to be this cross product from the previous formula. And so you get this really nice formula for the curvature if the curve is given by y equals f of x. So either f of x, or if you can break it back out into these two pieces here. So to use this one in just a couple formulas, a couple examples here. For example, we just said y equals 1 over x. So that curve, now we're going way back. No more vectors in this example, but so it just looks like, you know, half of a hyperbola if you turn your head sideways. It's the reciprocal curve, y equals 1 over x. We don't have any t's in here. And I don't know, the question is where is this thing look the most curviest if you were to actually draw it properly? I think as you come in towards the axis, it starts to look, it's an asymptote, so it starts to look straighter and straighter and straighter and straighter. And over here it looks straighter and straighter and straighter and straighter. So it's not, the curvature is going to be getting closer and closer to 0, because there'll be no curve to it. And so the curve is going to be somewhere here in the middle. And maybe not too surprising that it really is in the middle, because this thing is symmetric on both sides. So it's probably curviest like right in the middle there. But we can verify that by just computing this curvature. And it's a fancy K, again, it's kappa, it's the letter kappa. As I'm going to need the first derivative, and I'm going to need the second derivative. So in my kappa formula, the function is 1 over x, because that's y. I need f prime. So I take the derivative. I don't know if it's easier to remember, put that as x to the -1. We might as well. So we take the derivative, you get -1 times x to the -2, or just negative x to the -2. And then the second derivative, we just continue the process here. The -2 will come down to be +2 x to the -3. So let's see, my formula was I take the absolute value of the second derivative and divide it by 1 plus the absolute value of the first derivative squared raised to the 3rd power. So raised to the 3/2. So let's see, take the absolute value of the second derivative, I just get 2x to the -3. And in this example, I'm only going to look on the right side, so when I take the absolute value, I don't have to worry about it because all of the x's here are positive. In the denominator, I'm going to get so what am I going to get in the denominator? It's going to be 1 plus the derivative squared. So that'll be 1 plus square the derivative. Well, technically it's absolute value squared, but you don't really, I'm not going to need that for that example. And in fact, the absolute value here is not really needed. It's just kind of in there as a kind of a nice reminder. So if you don't want to write the absolute values in there, it's okay. Because when you square it, it's going to work out anyway. So when I square this, I'll get x to the minus 4, and then raised to 3/2 power. So it's not super pretty. If you don't like the minus powers in there, I guess you could rewrite it as 2 over x cubed and 1 plus 1 over x to the 4th raised to 3/2 power. And I guess I could clean that up a little bit if I wanted to. And let's just do it for practice here. So I can write this as 2 over x cubed. Common denominator on the bottom will be x to the 4th plus 1 over x to the 4th raised to 3/2 power. And we're going to into a little bit of, come over here. So if I took this, I'd get 2 over x cubed all over, I could write that as x to the 4th plus 1 to the 3/2 power. And then what happens when I take the 3/2 power for x to the 4th? So this means take a square root and then raise it to the 3rd power. So that'll be x to the 4th, square root will be x squared, raise that to the 3rd power will be x to the 6th, and then I'll flip and multiply this. If I flip and multiply, I'll have 2 over x cubed times x to the 6th over x to the 4th plus 1. Hopefully none of these steps are not particularly hard. It's a pretty easy derivative, but you can get lost in the algebra usually. So if I cancel x cubed, I'll still be left with 2x cubed on the top, and on the bottom, I'll have x to the 4th plus 1 and 3/2 power. So if you wanted to figure out, we wanted to put in a couple of examples. For example, at x equals 1, then the curvature is 2 over 2 to the 3/2 power. So just plug in 1 everywhere. The top will be 2, the bottom will be 1 plus 1 to the 3/2 power. So I guess I could do some cancellation here. It's going to be 1 over the square root of 2 or square root of 2 over 2. And so at the point 1, 1, the curvature is square root of 2 over 2. And as I plug in different values, well, I don't know if I want to plug in. As x gets really, really big, this denominator as x gets really big, the kappa looks approximately like 2x cubed over x to the 6th. So if 1 is, if x is really big, this plus 1 is going to be irrelevant. It's going to get really compared to x to the 4th. So x to the 4th raised to the 3/2 power is x to the 6th. So this thing is definitely going to 0, just like I expect, because it's straightening out and getting more like the line. And if you were to try to find the maximum curvature, it does turn out to be at that point at x equals 1, or what is the point 1, 1. How do you do maximums? I don't want to do it, but you take the derivative, set it to 0, solve it out. I don't want to take a derivative of this kappa curve here. But that's the idea. We're going to do one more, and then we'll take a break here. And this is kind of the important one that should make complete sense. Like the star on this is, for example, suppose I did this example. RT equals, I'm going to use the letter A in here. So A times the cosine of t and A times the sine of t. So this picture should be pretty familiar at this point. Circle of radius A, and the question is what is the curvature formula for that? Before we compute it out, if you look at a circle, where is a circle more curvy than at other places? And hopefully you realize, well, it's kind of the same curviness all the way around. So if that's the case, then the kappa curve, the curvature of this thing, should never change. It should be one number because it's the same curviness all the way around. We should have the same curvature all the way around. So the k should end up being some constant. But is that constant A? Is it like, or is it some version of A? Does it matter what A is, or is it, I don't know. But I don't know, let's see. What happens if A, if A is small, then you're gonna get a small circle. And if we go back to these tangent things, remember, it's like, how much does that tangent turn as you go one unit around? So in a small circle, the tangent thing is changing really radically. If A is big, then that means the circle is much larger. So if I have a tangent vector here, and I go one unit along, and I draw a new tangent vector, it didn't change very much. Whereas over here, if I went one unit, the tangent changed quickly, whereas down here, the tangent doesn't change very much. So that must mean that the curvature is bigger for the small circle than it is for the big circle. That's sort of the intuition here. It's like bigger circles are sort of less curvier. It's like the Earth, right? The Earth is flat. Let's just look outside, it's flat. Well, that's just because the Earth is huge. And so it looks locally linear. Anyway, that's too much on that. But let's calculate the curvature of this using R prime, R double prime, and the cross product and all of this stuff. So very familiar with all of these. The derivative is minus A sine, A cosine, the derivative of that. So second derivative, we'll be back to where you started from, minus A cosine, with minuses, right? Minus A sine. And now the curvature formula, I need the cross product, and I need some of these lengths. So that's doing that. The length of R prime cross R double prime over the length of R prime. So let's find these things real quick. R prime cross R double prime. Now you're like, well, wait, there's no K component. So that's where you have to stick in the K component being 0. So I, J, K, R prime will be, I might have drawn this too small, but we'll see. Minus sine, A times minus sine, A times cosine, and then 0. And then minus A cosine and minus A sine and 0. And so that's the cross product. And this one, if you do I and J, there's nothing because these zeros in the K component will kill it. This also should make sense. If you have something in I and in J, and you do the right-hand rule cross product, it's going to point directly straight up. So that means it's only in the Z component or only in the K component. And so everything is gone except for K. And if you do this little subdeterminant, yay, we get A squared sine t squared, and we'll get plus A squared cosine squared in the K component, which is just A squared in the K component. That's squared. A squared in the K component. So that's pretty nice. There's the R prime cross R double prime that we're going to take the length of in a second. The length, we're a little bit all over the map here, but the length of R prime, yay, same thing. It's the square root of A squared sine squared plus A squared cos squared. And that's equal to A. because it'll be a squared under the square root, and so that's the efficient way. So here's the big deal. If we put this all together, then k, which is the length of your vector r prime cross r double prime, will just be a squared. You can do it, the length of this is just a squared. R prime, in the formula says I just divide that by the length of r prime, a cubed. And I end up with the magic formula 1 over a. So for a circle, here's the star thing to stick in your head and remember it, is for a circle, the curvature is equal to, it's the reciprocal of the radius. So, I'll just write that in here. It's the reciprocal of the radius. So if you have a small radius and you take the reciprocal, the curvature gets big. If you have a big circle, then the radius is big, but you take the reciprocal and the curvature is small. And so that sort of just goes along with our intuition. The big ones, the tangents don't change very much, therefore the curvature is not as big, it's not as curvy. And this is one that maybe you already have come across or seen, but it is constant, and it does make sense according to, at least will be sort of reasoned out based on the definition. So, if you're still with me, hanging in, not dozing off, that's pretty much that section in there. We can do some more examples, but we're going to come back after a short break and talk about the test, go through some homework questions that some people had problems on, answer a lot of questions that you have for tomorrow, get you all caught up. If some of your homework is late, I really want you to get it done. Again, if you do it, pretty much just 10 out of 10 for effort. Doesn't mean you got it right. So that's what we're going to do when we come back. So maybe 8:20, we'll see everyone back here, and then it'll be hopefully a lot more of just me talking. My voice gets tired. So, see you at 8:20.